pictures. I thought they were kind of cool. Okay, today we're talking about congruent and similar solids. Okay, this will be our last lesson for a couple of weeks. Okay, yay. Okay. So we want to first talk about what similar solids are. Similar solids are a lot like figures. Okay, two solids are similar if they have the same shape and the ratio of their corresponding linear measurements are equal. So basically, each one of their linear calculations or linear measurements are proportional. They have the same scale factor. Okay. So like here's a rectangular prism in blue, and so your length 1 to your length 2 is to your width 1 to your width 2 as your height 1 is to your height 2. If you write all of those as a ratio, they should reduce to be the same amount or divide out to be the same decimal. Okay. That makes them similar. Okay. Here are cones. You could probably look at your slant height too. If your height and your ratio had the same scale factor, your linear, your slant height would follow suit. But your height to your height, your radius to your radius, and then the slant height to the slant height. It'd be the same with the pyramid. There's 4 things you could look at in a pyramid because you could do the length of the base, the width of the base, the height, and the slant height. But anyway, and then you also have your cylinder, and you would look at the height and the radius, and they would have the same ratio if they are similar. Okay. All spheres are similar, no matter what. Okay, don't forget this because there's a problem in your homework that asks you about this. All spheres are similar. Okay. All right. Congruent solids. Those are solids that have the same shape and exactly the same size. So they're going to have the same radius, the same slant height, the same height, same width, everything. They have everything exactly the same. They have a scale factor of 1 to 1. Then they're considered congruent. Okay. Spheres with the same radius are congruent. Okay. Spheres with the same radius are congruent. All right. So let's look at these and determine whether or not these solids are similar. This is really easy. We have 2 rectangular prisms. Okay. And here they give us the length, so we could set up 2 to 5. And then we have our depth or our width, 8 to 20. And then we have our height, which is 6 to 15. I should be able to divide those out or reduce those fractions. And if they're similar, they're all going to be exactly the same. So if I reduced all these, they would all end up being 2/5. If I divided them out, they would all be 0.4. Okay. And so we can make a statement that all lengths have the same scale factor. Therefore, they are proportional. Okay, look at the second one. Am I going to do 8 is to 5 as 15 is to 13?
No.
Why not?
Okay,
Okay, one of them's a height and one of them's a slant height, right? Okay, so I would do the Pythagorean theorem, and I could get my slant height here to be 17.
Well, the other one's a triple.
The other one's a triple too. This one's a triple. 8, 15, 17 is also a triple.
Oh, well.
It's not one we use all the time. Okay, all right. So, and that one's a 5, 12, 13. So, even if I just compared, if I went radius to radius, 8 is to 5, and then height to height, 15 is to 12. Is that going to work? It's not going to work. I could cross multiply or I could reduce. This one can't be reduced, but if I reduce this one, it ends up being 5/4. Okay. All right. So we would say the lengths are not proportional. That's right. Proportional. Therefore, cones are not similar. The lengths are not proportional, so the cones are not similar. So that part of it's pretty easy. Okay.
That part of it.
That part of it is pretty, and this other is not horribly hard. It's just a little trickier. Okay. Now you remember back in the last chapter when we were given like areas and we were maybe given a side length, and we said that the side length was not directly proportional to the area, right? What did you have to do to the side length? Or the scale?
Square it.
You had to square it. You had to square the side length or the scale factor in order to set it up a proportion for the areas. Okay? Surface area is the same thing, okay? And volume both, okay? They do not have a direct relationship, okay? This theorem says that if two similar solids have a scale factor of A to B, then the surface areas have a ratio to A squared to B squared, and the volumes have a ratio of A cubed to B cubed, okay? So, you have your scale factor, which is, A to B. It's also worked for the side lengths and the perimeters, okay? It has a ratio of A to B. It's proportional to the area, but you have to square the scale factor, and it's going to be proportional to the volume, but you're going to have to cube the scale factor, okay? They do not have a direct relationship, okay? So, if you have a scale factor, it's proportional to the area squared into the volume cubed of that scale factor. So, let's look at this right here. What would my scale factor be between 9 and 6?
2/3.
Okay. Okay, I go left to right. 3/2, 2/3. If it doesn't specify, it doesn't really matter, I guess. Okay. So then, if I want to do a ratio of the surface areas, I would take that and I would have to square it. So it would be 9 to 4. What? Or 4 to 9 if you did it the other way around. Okay, and then the ratio of the volumes would take both of those and cube it, which would be 27 to 8. Okay? All right, so in your homework today, they're going to ask you for the ratio of the surface areas. Okay? And so if you're given side lengths or you're given a scale factor, you have to reduce it. And for the ratio of the surface areas, you square that. Same thing with the ratio of the volumes. If you're given the scale factor or the side length, you write it as a ratio, you reduce it, and then you cube it to get the ratio of the volumes. Okay? All right. So let's look at this first example here. It says two similar prisms have a surface area of 98 square centimeters and 18 square centimeters. What is the ratio of the height of the large prism to the height of the small prism? Okay, so it gives me the surface areas, and I want a ratio of the heights. Okay, so the first thing I'm going to do is I am going to set up a surface area ratio. So that means that I take my surface area and I write them as a ratio. Now it wants it from large to small. Okay, so the ratio of my surface areas would be 98 to 18. Okay. Then I'm going to reduce, if possible. Sometimes you can't reduce, but reduce if possible. And this one can be, right? What goes into both of those?
3.
2 does, definitely. I don't think 3 does. Goes in there 9 times, and that goes in there 49 times.
Yeah.
Okay. So I set up the surface area ratio, I reduce it, and then I take the square root to find the scale factor. So I did my surface area ratio, I reduced it, then to get my scale factor, I'm going to take the square root, and it's going to be 7/3. That scale factor, 7/3, is also the ratio of the heights. Okay? All right, look, here's another one. The surface area of two similar figures are 16 centimeters squared and 49 centimeters squared. The volume of the larger is 268 centimeters cubed. Find the volume of the smaller. Okay, so what we have to do here is we're given surface areas and we're given one volume. Okay, I need to find the other volume. So what I have to do is I have to take the surface areas and break it down to find the scale factor. Once I get the scale factor, cube it back up to set up a proportion to find the volume. Okay? So, first thing I do is I set up a surface area ratio. Okay? So here's my surface area ratio. Okay, I've got 16 to 49. That's the ratio of my surface areas. Okay? I reduce if I can. Can't reduce this one. Okay? Then I take the square root to find the scale factor. Okay? That's exactly what I did up here on the one before. It ends up being 4/7. That's my scale factor. Okay? All right. Then I cube the scale factor to set up a volume ratio. So I take my scale factor and I cube it, and that right there is my volume ratio. And then I set up a proportion with the volume. Okay? So, I've got 4/3 over 7/3. Which volume do they give me? The larger one. Okay? So it's going to be 2/16, and I'm going to let X represent the smaller one. Okay? So now I've got my proportion, and I can solve. So this right here, 4 cubed is 64. 7 cubed is 343. And I have X over 216. I'm going to cross multiply. 216 times 64 is 13,824 equals 343X. Do I have a terrible? 13,824 equals 343X. Divide both sides by 343. And X is 40.3 centimeters cubed, which is the volume of the smaller. Okay, so I was given the surface areas, and I was given one volume. So I took the surface areas, reduced them, couldn't be reduced, took the square root to find the scale factor. Once I got the scale factor, I had to cube it back up for the volume ratio, and then set it equal to a proportion with the volume, and solve. Okay? All right, let's do another one. The containers at the right are similar cylinders. Find the height of the smaller cone. Okay, so now disregard the fact that it's a 10-foot oil barrel. That's pretty big. Okay, you know, look at that. All right. Now, your height and your scale factor are proportional. So instead of using scale factor, I can use height as well. It's not going to make any difference. Okay. Probably the first thing that I would do is take my height, okay, which is like my scale factor, and I would cube it. Okay, I'm gonna do a ratio of the height, and I'm gonna do 10 cubed is 2h cubed. Okay, so I'm going to cube my height ratio. And then I'm going to set up a proportion with the volume. So I cube my heights, and then I'm going to do the volume of one is to the other. Now I might do a little bit of simplifying here. What could I do with my pies? Cancel. I could also get rid of that 0, couldn't I? Okay, and then this would be 1,000 over h cubed equals 64 over 27. And I'm going to cross multiply, and I get 27,000 equals 64 h to the third. And I'm going to divide both sides by 64. And it doesn't go evenly. Okay, so I'm just going to leave it as a fraction, and then I'm going to take the cubed root of that fraction. Okay. Now, some of your calculators, when you go to find the cube root, it'll have like a little button like this. Okay, and so you would do 3. Let's do the cube root of 27. Okay, the cube root, you do 3, and then you would press that button, and then you would press 27, and it should give you 3. If you have a graphing calculator, you may have a graphing calculator. Okay, you need to hit the math button right here, and then arrow down till you get to the cubed root. Press it, and then hit 27. Okay, and you should get 3. The cube root of 27 is 3. Everybody find that button on their calculator. Okay, so now the other thing you got to remember when you do the cube root of a fraction is that you have to put it in parentheses. You have to put the division in parentheses. So you would do the cubed root, and then you would open a parenthesis, and you would do 27,000 divided by 64. And the answer you should get for the height is 7.5. Oh my goodness. Okay, yes. Did you get the same answer? Okay. You can use the cube root, the volume. Yeah, and then you did a direct proportion. Yeah, that worked too.
Hey, Maddie.
He said he took the volumes and took the cube root of those and got the scale factor and then set up a direct proportion with the heights, and that would work too. Okay. All right. It works nice if you can actually take the cube root of those numbers, but if you couldn't take the cube root of those numbers, it does get a little bit messier. Okay, so. Oh, Bridge. Oh, it would be. You're right. Feet. Thank you. Thank you. All right, let's do another one. Oh, okay, it says the volume of two similar figures are 125 inches cubed and 343 inches cubed. The surface area of the smaller figure is 625 inches squared times the surface area of the larger figure. Okay, so what they do this time is they give us volumes, okay, and they give us the surface area of one. We want the surface area of the other. So it's kind of exactly opposite of what we did in the problem, like 2 problems ago. So the first thing we're going to do is we're going to set up a volume ratio. Okay, so my volume ratio, I would do the ratio of the volumes, which is 125 over 343. Okay, I would reduce that if I could. You can't reduce this one. Okay, and then you're going to take the cubed root to find the scale factor. So I do the cubed root of both of those. Okay, cube root of 125 is 5. The cube root of 343 is 7. Okay, and I wouldn't do the cube root of the whole, fraction. I would do each individual one, especially if it looks like it might work, unless you have you know how to work the fraction part of it. All right, so this right here gives me my scale factor. Okay, then I want to set up a surface area ratio with the scale factor. Okay, what do I have to do to it? I have to square it. So I take 5 squared over 7 squared, and then I can set up a proportion with the surface area. So I do 5 squared to 7 squared, and then I set that equal to, they give me the surface area of the smaller one, so it goes on top, and there's the surface area of the larger one. So I have 25 over 49 equals 625 over x. Cross multiply, it gives me 25x. 49 times 625 gives me 30,625. divide both sides by 25,
1,225.
and you get 1,225 inches squared.
Hold on.
Okay? All right. So, if you have a height or a scale factor, what do you do to get a surface area?
You square.
Volume. A surface area ratio. You square it. To get a volume ratio, you cube it. Okay. If I give you surface areas, and I give you one volume and I want the other one, what do you have to do to the surface areas?
Square. No.
Reduce and take the square root to get the scale factor. Then cube it to set up a proportion with the volumes. Okay? Now, if I gave you the volumes, and I gave you one surface area, right? What would you do to the volumes? Set up a ratio, reduce if you can, take the cube root, that gives you the scale factor, and then what would you do? But you have to square that scale factor before I set it up with the ratio of the surface areas, or proportion with the surface areas. Yes? For surface area, I mean, for scale factor, it has to be fractions. And you can't have a decimal within the fraction. Okay? So, like, if you had 2.5 over 5.5, okay? And that was your ratio, and you want to scale factor. What do I have to do to this? Multiply both the top and the bottom by 10, or you could really multiply by anything, but you're just moving the decimal over. So you end up with 25 over 55 and reduce. Okay? All right? All right. Any questions?